Yep, Jennifer did a great job. I'm sure with a bunch of other people that she worked with to put that newsletter together. It comes out at least once a month. Lots of great events and just more information about our events too. Is there anything else to add on that? Tonight's event is being recorded. We're going to be posting it to YouTube, so that's going to be new with this new space. We used to do that when we were back at the Lighting Children. So that's awesome. And we already talked about drinks after. And our next meeting, I can touch on at the end of this presentation. And so just to start us off, I'm going to talk about the passive house requirements for airtightness testing, and then I'm going to turn it over to Mark. So the agenda is what I just said on my side. Mark is with UL, and he's going to be talking about the on-site and off-site testing that you can do during or before construction to help your project reach the FIAS Plus airtightness target. And then Lindsay with EcoAchievers is going to talk about the blower door test that she has done personally. So we have 3 presenters. So what the FIAS Plus requirements are for airtightness are listed here. Please note that it's based on stories. And so if you're a 5+ story building, it's less than 0.08 CFM at 50 pascals. It's a little bit more stringent in a smaller building. And so today we're just going to focus on the airtightness aspect of passive house here on the bottom right. I put in just some comparisons like what the Chicago code requires and what ASHRAE requires. And what's interesting is that ASHRAE 90.1/2013, which is optional to follow as one of the energy codes in Chicago, does require a continuous air barrier, but there are different meanings to what that air barrier could be. It doesn't have to be like a fluid applied. And then the Army Corps of Engineers is probably the most stringent, other than passive house, in terms of airplanes. So we're pushing the envelope literally here, but what we can see on this slide is that it's achievable. This is the Cornell Tech building that just completed construction in New York. It is meeting the airtightness requirements. I hear that it's a super airtight building, both on the envelope and on the mechanical duct side. It's over 20 stories. It's going to be the world's largest and tallest, maybe not the tallest, but the largest passive house project. So that's awesome. So I'm going to turn it over to Mark, and he's going to talk about the on-site and off-site testing. Any questions so far?
I like what Sean said at the beginning about this being a very casual, informal environment. I really like you guys introducing to that. It's a good thing. Anyway, if you have questions at all as we go, just pipe up and ask us. It's small group needs to handle that. A colleague of mine did a presentation recently at AIA on a very kind of similar topic in a way. So I kind of feel I have to apologize. You might, those of you, if any of you were in attendance at that, you might find some similar content here. Tim was in attendance and asked us to present today. Obviously, we accepted, so here we are. We have tried to sort of focus today, refocus the presentation on air barrier, air tightness, and some of the measures you can take to hopefully achieve air tightness in your construction. So hopefully a few nuggets, new nuggets here for people who are also at the AIA. So my name is Mark Van Dalen. I'm with CLEB. And in terms of an agenda, I'm going to do a bit of shameless marketing off of that, just to do a little bit of what the CLEB is all about. I'm going to spend a bit of time talking very quickly about what an air barrier is, why it's so important, and just how you go about integrating it with design. Tim asked that we have a bit of time talking about one particular type of wall assembly that consistently achieves very high performance with air tightness. And then I'm going to talk about some of the measures that you can take during construction to hopefully end up with a good airtight build. That includes laboratory testing, field testing, and I mean field testing of an actual specimen, and then also thermal imaging to detect any problems. We've already got ourselves a bit out of sync here because I thought Tim was going to be talking at the end about passive house requirements. He's already done it, so ignore that last bullet. So UL CLEB, hopefully you all know UL already. It's been an organization that has for decades been spending time researching and doing testing so as to, their focus has been to make our buildings safer from a life safety perspective. We are the division of UL that does the same thing, hopefully, with the focus on the building envelope. So testing and advisory services to hopefully better performing building envelope assemblies. We have two large full-scale testing facilities, one in Northbrook and one in Montreal. And then we have in the other office locations, we have staff that just get involved in the advisory side of the services where we do most of more consulting to clients like architects about envelope issues or building owners who have problems with their building envelope that's already being constructed. So as they say, I call it Chicago, it's in fact Northbrook. There's a 63,000 square foot facility over there where we do full-scale mock-up testing. If any of you ever want to go and see it or a tour or anything, we're more than happy to receive you and let you come and have a look at what the tests. Any given day, you may see something different, depends what's going to go through at the time, but you're more than welcome. You're also welcome in Montreal if you want to come up that way, but I realize it's a little bit further afield. Montreal's a little bit smaller in terms of total testing. You'll notice in the Chicago one, it's the building, and all the testing is done in-house inside in Chicago, which is very nice when you have a cold climate to deal with at certain times of the year. In Montreal, we have indoor facility as well, but a large number of our chambers are actually outdoor. Causes a little bit of grief. It's very, very cold. Water freezes before it goes through the walls. Anyway, that's about us. You all know, I'm sure, what building envelope is. I've just put this one slide in here. It's the physical separation between the conditioned indoor space and the unconditioned environment. And it's got to hopefully resist the transfer of a lot of different things, including air, water, heat, light, fire, noise. So this is just a little schematic we have just to kind of illustrate that as the fundamental requirement or objective of the envelope. And this slide just shows you the same schematic, but it also shows you in the table the list of all the things that are really required in an envelope. And the list is quite long. Structural, it's got to carry the loads that are imposed on it. Heat flow, airflow, moisture flow, and moisture both in liquid form, so that would be rainfall and snowfall instead of precipitation, but also in vapor form. So more and more these days, we want to make our buildings comfortable in the wintertime, so we put air, sort of water into the air. Well, that's a load that the envelope has to sustain in some manner. Solar radiation, sound transmission, fire, durability. More and more there's a focus now on making sure our construction is durable. But it's also got to be secure. Unfortunately, there are risks in the world today that we have to worry about. Economy. Budgets aren't always there for building the top notch, so we have to be conscious of the costs, both in terms of building in the first place and what it's going to take to run the thing, to maintain the thing. And then there's the environmental impacts, buildability, and of course aesthetics. And the little schematic at the bottom left is just there to remind me and tell you that it's often a balancing act. So when the budget comes out for a building or a certain build for the envelope, like any other systems, you can't necessarily hit the top end of the spectrum on all of these aspects of performance. And so depending on the use of occupancy and the design service life, you sometimes end up balancing between some of these various requirements, making sure that you end up with something that will give the client what they need for the duration of the time they're hoping to use the building at a reasonable cost. But today we're just going to be talking about airtightness and air barriers, just because it's the thing Tim thought was the most topical and most appropriate for this group. So the first thing that I just wanted to highlight for you is what is an air barrier and why we talk about an air barrier as distinct from a vapor barrier. The reality is that probably prior to 1985, I'm not aware of any code that said very much about building envelopes. If it did say anything, it would probably only have been about some insulation to keep us warm and a vapor barrier. And the reason behind that is that when problems first started to show up with building envelope, then there were moisture problems. The researchers decided at that point that the problem was the diffusion of moisture from inside the space. And so any material that we put in an exterior wall will have some characteristic in terms of vapor permeability, and it means it's the rate at which vapor in the air can move through those materials from higher vapor pressure to lower vapor pressure. So in the wintertime, pretty much all of our homes and all of our buildings have a high vapor pressure inside, and that means that the vapor will slowly diffuse through the materials to the outside. ironically, in warmer climates that we are now getting to deal with really well, the problem is the reverse. In a lot of the warm tropical climates, the moisture load is the reverse. It's a higher vapor pressure outdoors, and the problem is the vapor getting into the building and having a real problem controlling comfort levels inside. But for climates like Chicago, it's pretty much always the other way around. And so from a diffusion point of view, they said, well, you know, we really better start putting a vapor barrier in there, and it's a material that's going to be impermeable or close to impermeable to vapor, and it'll cut down the problem. And so that's where they started with in most codes. And the problem was that after a period of time, they realized that the moisture problems didn't really go away. And so they sort of scratched their heads and said, well, how can this be? We thought we had it licked. And they did further research, and upon further research, they realized that the vapor diffusion mechanism exists, and it's real, but it's not nearly as significant in terms of how much moisture can move as air leakage. And so this little slide shows you that on the right-hand side, if you're dealing with diffusion, it's the amount of moisture you can move is a direct function of both the characteristics of the materials, so how impermeable they are to moisture, but also the area. And so if I have a 3 meter by 3 meter square section of wall with a few coats of paint on it, and I did this for a calculation for a cold winter climate, in one heating season, by diffusion, you're going to move about 1/3 of a liter of water through that section of wall. And even if you had a little opening or a little discontinuity in that vapor barrier, because the area of that would be very small, it would make hardly any difference. There'd be almost no change in how much moisture can move through it. In contrast, if you take the same 1 meter or 3 foot by 3 foot wall area, and you put a 1 inch hole in it, 1 inch square hole in it, and now you take a pressure differential, and a pressure differential can be created by a mechanical system, if it's a big building, or it could be created by stack effect if it was a tall building, or it could just be wind effects. So any pressure differential, and I did this calculation just for a 10 Pascal differential, which is really, really low. But through that 1 inch by 1 inch hole, at 10 Pascals, over the same winter time, you get about 30 liters of water. And it's because the moisture is being transported in the airflow, and the mass transport of that water ends up being far more water that was going out through the hole than you'd ever get by diffusion. And so they realized that, gosh, if that's the case, we got to stop that airflow, and hence the reason for an air barrier. So we now have, in a lot of codes, a requirement for a vapor retarder or vapor barrier, as well as an air barrier. The difference being that if you have a small discontinuity or a small opening or something in your vapor barrier, no big deal. But in an air barrier, it's going to be a big deal on a cold climate. So you have to absolutely get continued continuity in the air barrier system. It's got to be something that's impervious to the air and that can stand the pressures of the wind so that the air doesn't flow, and it's got to be continuous. And this little slide is just a schematic. It's a vertical cut through a very common residential wall assembly. Brick exterior, airspace, a frame stud wall with insulation in the framing, and then schematically we show on the inside that there is both a vapor barrier and an air barrier. And what we're depicting here is a break in that air barrier, which is an unsealed electrical outlet. So the fact that that would be a break in the vapor barrier would really give no consequence. But what happens is, if that exists and we are continuously flowing moist air through those gaps, it'll come back and it'll eventually contact a cold surface, which might be the exterior sheathing of the framed wall, or it might be the inside face of that masonry, and it'll drop that moisture. And it'll drop it in liquid form if it's cool, or it'll drop it as frost or ice if it's cold. So climate like we're in here, the last few days, it's going to drop it as ice, and then when it warms up a little bit, it turns back to water, and lo and behold, there's the source that causes all the degradation. So Passive House has an element, if you look at the documentation, has an element or a bit of discussion about the concern of air leakage as it relates to moisture deposition in your wall and why you want to prevent it. But they also, and I would argue maybe more so, concern themselves with the fact that we've paid money to condition that indoor air. We've paid money to raise the temperature and to put humidity into it. And therefore, as the air and the moisture flow, money is flowing as well. So from an energy efficiency and from a cost perspective, the air barrier problem is not just a moisture problem, but it's a real dollar problem as well. This is just a shot that I took that I think is really a good illustration of the problem. This is a metal glass curtain wall. As you can see, it's the bottom of a wall system. There's a ground floor or sort of overhang or setback of them. And this is after a prolonged period of cold weather. There had been no rain, there had been no snow that could have melted it, and yet there are icicles hanging out the bottom of this wall. So those icicles are the direct result of air leakage. Water that was in the air inside was blown through the assembly wherever the holes existed, condensed on the cold metal surfaces, and formed at the edge of the building like this. And I was smiling as I was walking here today, because as you walk along the sidewalk, just a few blocks from here, there are signs saying, beware of ice overhead. So this is a real problem, because if these things are growing and then falling on you and I walking along the street, building owners have a problem on their hands. So it's not just durability that's at risk here. So I guess the question is, well, how does this air barrier concept get integrated into the design? And it really isn't rocket science. When a designer is planning their work and thinking through their details and whatnot, they simply have to have it in their head that there is another element to the overall assembly that they have to incorporate throughout the entire design. And that's an element, as I say, it's got to be continuous, it's got to be impervious to air, and it's got to be able to carry the load of the wind. So during the early concept development stage, what often happens, and this is just a couple of sketches that are examples of it, but you often have a selection made of the kind of materials, the kind of systems you choose to use, sort of the massing and the general layout. And the idea is that you need to be sitting down at that point once you've got those basic premises laid out and making sure that you've incorporated something that joins them all together. And it doesn't matter what kind of material you're going to be using per se, as long as it meets the characteristics that I laid out, but you need to be able to see that there is continuity of panels to windows to doors to all of the different components you've chosen. And so this is the type of thing that often happens where the architect will sit down with the colored pencils and whatnot, and they'll actually sketch out in different layers, different colors, to make sure that they can visualize where all the air barrier elements are going to be and what they're going to be. And sometimes it's not just one. This is an example where this is the mullion for a glazing system, this is a structural steel element, and this is going to be the part of the air seal joining into. So the air barrier here is in fact a combination of the aluminum framing, the membrane, whatever they use to join the aluminum framing to the steel element. So it could be a whole combination of materials. Once that concept's developed, and I don't expect you to be able to see this very well, but once the concept is developed, that of course has to be translated in some manner into the working drawings. Because at the end of the day, the working drawings are going to go to the GCs and to the trades. That's what they're going to follow to build the thing. So this is a vertical section cut through the exterior wall where the middle floor projects out past the floor above and below. So we end up with a terrace here and a soffit here. And I could have chosen any drawing, but what you need to be able to do is when you look at this drawing, you need to make sure that the concept that you've developed at the beginning about continuity is followed through appropriately. So that every one of these details has an element in it that is airtight and show continuity. And I often say to people, if you can take a red pen and you can draw one line with your red pen from the beginning to the bottom, and it never stops anywhere, you've got continuity. But if you can't draw it, because there's some gap of some sort, you run out of material that's impervious, for example, you've got a problem. So you've got to have a continuous red line. And it doesn't matter whether it's this profile or a roof wall junction or a much simpler, straightforward, just planar wall. It's always the same idea. There needs to be something in there that you can look at to see this connection between all the different components. So there, of course, are a myriad of wall systems that designers can choose when they go to commercial wall construction, for that matter, residential as well. Masonry systems, precast systems, eave systems, individual windows. But Tim asked me to just have a few moments to talk about a system that seems time and time again to give us the very best performance if you're talking about commercial wall assemblies, and it's unitized metal glass curtain wall. And I'm talking here about Airtight performance. It also has good performance in other characteristics as well, but in terms of Airtightness, it's the one assembly that is probably easiest for the architect and for the builder to know that they're going to reliably get good performance at the end. And there's a pretty good reason for it. So if you know about unitized curtain wall system, and jargon changes from location to location, but it's basically made up of either a bunch of different units, or you call them modules, or you call them panels, panels, or whatever you want to call them. But these individual panels, modules, units are pre-assembled and prefabricated off-site in a factory. And they're then brought to the site on a truck, they're hoisted up, and they're assembled together, kind of like Lego blocks in a way, and when they're all put together, you've got your exterior wall. Really, really attractive because, well, for a number of reasons, but number one, they don't take any space on site. They can be under construction, under fabrication while you're doing the structure, so there's no scheduling issues there. And it means your building can be enclosed extremely quickly, because as fast as you put the panels together on the wall, you're closed in, as opposed to bringing the individual components to the site and having to put them all together. So they're very attractive from many points of view. So here's just a schematic, and the modules take all kinds of different shapes and all different forms. They have all kinds of different materials in them, but the basic premise is the same. You decide on what the module overall size is going to be, and typically they're constructed on horizontal tables. So there's a line of flat tables in front. And the framing around the perimeter of the module, they're all open. By that I mean they're basically a half section, because they're going to snap together with the making half of the adjacent panel when they get put together on the wall. So perimeter frames are all put together. Any internal intermediate frames are solid sections. They're also laid out. And these things are all assembled on the flat and screwed together. And most importantly, for today's discussion, all the seams are sealed, all the screw heads are sealed, all the framing is sealed together so that you can be confident that there's no leakage paths. Yeah. Yes?
Material of preference is what?
For the framing?
Yeah.
Virtually all panel system for metal and glass is done in aluminum. There are panelized systems now coming out that have, well, for example, East has been panelized for some period of time, and people are now doing it even with steel stud framing with either ACM panels or aluminum plate panels. But the most common unified system is aluminum framing, and then in the openings, which is where I was going next. So you have defined the openings with the aluminum framing, and then inside the openings, you glaze in a panel of some description. So it could be a vision unit, an insulated glass unit, or it could be a insulated back pan, and over the face of that, you might put metal, you might put thin veneer stone, you might put more glass. But the point is that whatever you're putting in terms of a panel is also sealed in the factory to what has already been sealed as a framing element. So all those critical seals that are so important to us from an airtightness perspective, they're all done in what is presumably good quality control inside the factory without any fighting against Mother Nature and inclement weather. And you're not dangling on a swing stage, you're on some rickety scaffolding, you're solid feet on the ground beside a work table. So this element comes off the line as a very, very robust element from the air barrier point of view. And when they get to the site, basically they're installed in horizontal bands or rows around the building, and then you sequentially put row upon row as you go up. So here we've got one row in position and the first panel on a higher row installed, and what we're showing is the next panel is going to come along. It's going to snap together and interlock with the mating half on the vertical edge of the panel that's already installed. And once that's interlocked, it's going to be dropped down vertically to engage and interlock with the top of the panel below. Now, all of these joints between panels have well-designed rubber gaskets in them. And so when panels snap together or stack on top of each other, it's not a lot different than when you close your car door. And there's a very effective seal. I don't know if anybody's ever had water leakage through their car door. It's probably not very often there. But there's a very effective seal. When you close the car door, you compress the seal. It's not a lot different with these systems. When you snap the making halves together, you compress a very good rubber gasket in there, which is a very good job of sealing. And when you drop the panel down, it sits over top of a gasket, which is also now compressed by the load of the panel. So you also have a very good seal. So you've got a very nice system now, because within the panel, all the critical joints, seams, screw heads, everything else, panels to aluminum, that was all sealed in the factory. And on the site, all the primary joints between panels are sealed in a pretty reliable manner with the gasketing. And what you're left with is the lone pinch point is the four-way intersection. And that's because at that point, you've got vertical gasketing and horizontal gasketing that somehow has to join together. And sadly, we don't have a completely high-tech solution for that yet. It basically relies on caulking or sealant still. So these two little schematics just show you the idea as to how that's achieved. On the left-hand side here, in this line here, you would have a gasket between the interlocking panels. So this is the top right corner of one panel, the top left corner of another panel, and down this line, there would be a rubber gasket that's being compressed by the panels coming together. So that rubber gasket is brought up and turned over, and it's basically sealed in, using a caulking material, sealed in here to cap off that top end of the panel. And once that's done, they would typically bed a closure piece over that whole joint so as to reinforce the seal to make sure we have some belt and braces on the air seal, but also to make sure that from a water point of view, we're going to be able to deflect water back out of that joint. And the finished product would look something like this with a cover plate. In reality, most fabricators these days cover all of this up with a metal flashing as well, because it gives you a nice clean line in every panel joint. So what does it look like in reality? Here's a construction underway. So here's the panel that's coming up to the floor with the crane. You can see the panels are coming along installation this way. So it's brought up into position with the crane like this. It's brought into alignment with the adjacent panel. So you can see they're here making the interlock between this panel and the one that's already been installed. And it's obviously not yet finished installation because you can see it hasn't yet been dropped down into position. And here's the top side of one row completed. So all the panels on this band are done. If you look carefully, this is a gasket. This particular manufacturer supplies that gasket in 100-foot lengths. So when a row is finished, they literally unroll 100 feet of rubber gasket, put it on the top. There are no seams except for every 100 feet. And that's what's going to ultimately be compressed when the next row sits down on top of it. This is the metal that I told you is commonly installed over top of each row. And this is the very high-tech gob of sealant that is bleeding out from that four-way intersection that I described. Here's another shot of in progress. This particular system, the gasketing, the horizontal gasketing is installed in the factory on the panel. And so when you get to a joint, this blob of sealant, that's what's installed to achieve continuity of that gasket across the panel joint. And this panel is just about to come down. So everything is ready to receive it. It's already interlocked on the vertical. It'll be dropped down and it'll sit, the bottom of this panel will sit on either the gasket here or on the sealant at the intersection and achieve continuity with the air barrier that way. And the gasket in the vertical will come down and sit over top. And that gasket, I don't know if you can see this or not, but here's the horizontal rubber gasket that's already installed on top of the finished row. And this black line here, that's the gasket on the vertical edge of the panel. And if you look very carefully, it just comes over and basically the two gaskets overlap and pinch together. That's the only weak point, as it turns out, in the whole assembly, the only place where you might have some problem. Because if the two gaskets, if one rolls a little bit, or if the two gaskets don't have enough compression on each other, just at that intersection is where you might have a bit of a problem. And so, to overcome that, they loop it. So here's, seeing this in two different views of the same shot, but you can see the two gaskets are overlapping interlocked here, and this is the loop that goes in just to kind of seal it up and hopefully take care of anything that might exist. But that's pretty attractive, because that means now with a single supplier, right, there's not multiple trades involved in this, for a single supplier, what you're left with is in that entire wall face, and this could be 30, 40 stories of building. The only areas that are left over as a risk to you from the Airtightness point of view are those individual points in each intersection. Which, I mean, I'm not saying that we can ignore it, but compared to the risk of having a discontinuity in field-applied tapes or field-applied caulking or whatever the case may be over the same wall area, it becomes a very, very attractive system. There's the group at the end of the panel. So, if you're looking for a system that's giving you the best possibility, the best chances of getting a very, very perfect construction, you guys know that's certainly one thing that gives me serious consideration to. So, the next couple things we want to talk about are the measures that you can take to hopefully end up with good construction, good airtight construction, regardless of what assembly you've chosen to use. And so the first thing we're going to talk about is laboratory analysis. And this slide depicts sort of a whole range of things, actually not all of them, but a range of things that we can test in the lab facility. And it includes thermal characteristics, acoustic characteristics, water penetration performance, all those things that were on that list before. But we're here today to talk just about air barriers. Here's a slide just to give you an idea of what these mock-ups look like. These are purposefully selected to include virtually all the details you're going to encounter on the site. So the idea is that when you look at the mock-up, you've tested everything that you're going to build. Now it's not going to be exactly the same layout relative to each other, but you'll have corners, roof connections, bottom connections, intermediate connections, so that you really mimic as many of the things that you're going to encounter when you build. So the mock-ups are constructed. This is one underway, and I wanted to just do this to explain to you exactly how tests are run. This white end wall, and this white back wall, and this wall, which is actually white on the other side of this, they're all steel plate, and that's our chamber. And so when the mock-up is outlined to us, the size of the mock-up, we literally move the sidewalls depending on what width the mock-up's going to be. So we have a team of welders, and those walls are moved around as required. And similarly, when the height is decided, we move this ceiling up and down. So some of the mock-ups are single story like this, some are 2 or 3 stories high. So we move all that around. Basically what we give is an opening in a box. So there's 2 ends, there's a back, there's a top and a bottom, and then there's one side of the box that has an opening, and the contractor comes and builds his specimen in that hole. This is almost finished, and you can see there's just got a few panels left to go here, but that's a single story mock-up, which is pretty much ready for testing. So we're here to talk about airtightness. The ASTM test for airtightness is ASTM 283, and on the left here is a schematic which sort of repeats what I showed you in the other slide. Our chamber consists of a ceiling, a back wall, a floor of course, and the 2 end walls that you don't see in this section. Connected to that chamber, we have an air supply. We can either supply or exhaust from the chamber, and that's because we sometimes want to measure air infiltration, air coming in through the specimen, and sometimes air exfiltration, which is air going out through. So the supply fan, the blower fan, can do in or out, and in line with the supply is a flow meter. So we know how much air is going in or out of that chamber. So it's really fairly simple. We have a pressure measuring device across the wall of the chamber. We adjust the flow of air until the pressure measuring device tells us we're at 50 Pascal or 75 Pascal or whatever. And when we hit that and maintain it, we read the flow meter. It tells us how much air we're losing through the chamber while we're maintaining that pressure. So here's a mock-up. This one happens to be 2 stories, as you can see. And it's all ready to go for testing. And you're saying, Mark, of course it's got plastic that can't be ready for testing. But the plastic has a fairly important function for us because try as we might, and we do try our best, our chamber construction is not perfect. There's bound to be some leakage through the chamber. We call it extraneous leakage. So before we actually test the specimen, we mask it. We sometimes hear it referred to as a tear or a mask, but we cover the entire face with 1 sheet of polyethylene film. And we then do a pre-test effectively, where we generate the pressure, we measure the flow, and we know there's no flow going through the specimen because it's got covered by a piece of plastic. Yes?
Who's planning on these chambers? Is it the manufacturer or is it you?
No, it's always the contractor who's going to do the build because you can imagine if somebody else builds it and it doesn't work, guess whose fault it is, right? So we do all the work to provide the chamber and get everything ready for it, but when the chamber is ready, they come in with materials and they do the build. And it's an interesting point because we're going to talk about field testing a little bit later on, but it's a good segue into it. Laboratory testing is of tremendous value in my opinion because it lets the stakeholders know that the system that they've selected, or the assembly that they've selected, will achieve the performance they want if it has been assembled in an appropriate manner. However, if you come to a lab and you look around, you'll notice fairly quickly that, number one, often they're built indoors. So that's a little bit of a benefit for them. There's very little pressure, usually, to build it. So a mock-up like this might take a couple weeks, a week or a couple weeks to build, and install it with their very best installers. Like the most senior guys from the company show up to do it, right? And it's all in the interest of passing those tests. And it's valuable, and it's valid, because it does say that if you do it the right way, it'll work. When you get to the field, all of a sudden you're not indoors, so you're fighting potential inclement weather. There's often time pressure schedules, right? People are pushing to get this thing done. We're usually behind and trying to catch up. And unfortunately, and no disrespect to the contractors here in the room, but unfortunately, we don't necessarily have a full slate of highly experienced people working on it. If you've got 40 or 50 guys working on the site, some fraction of those are going to be people who, they're maybe not, maybe it's the first time working on a football, maybe it's early on in their career, they just haven't got, maybe they're just not as conscientious as some of the others. So they come and they build it here, but they come here with their very best crew, and it's one of the reasons why I think it's invaluable, but it doesn't replace field testing. And I often get calls from people saying, we've got a problem with our construction, we can't understand it because we had it tested in the lab. Well, that's great you had it tested in the lab, because if you don't know that it can work at all in the lab, then you're maybe fighting out the lab. But if you know it worked in the lab and it doesn't work in the field, chances are it's not the system problem, it's a workmanship or install problem. So, here's another shot of the 283 test, and I just included it so you understand. As I say, we often want to know an infiltration rate and an exfiltration rate. So in this shot, the mask film, you can see it's being drawn into the specimen. So this is us finding the extraneous reading for the infiltration condition. And the same specimen, and here we're getting the extraneous reading for the exfiltration condition. So we get those extraneous readings, which is the leakage attributable to the chamber. We then rip off the polyethylene, do the same test again at the same pressure, get a different number often, and the difference between the two is what's attributable to the specimen. That's the key number that all the people in this room are going to be interested in. So that's ASTM 283, laboratory test, and it's quantitative. So it's determining an exact air leakage rate for comparison to a performance requirement in the standard or in code. What often happens is that when you get a failure at a laboratory test, I don't think anybody in this room can see air flowing unless there's something fluttering in it. So the contractor normally is frustrated because he's just got a failure and he doesn't know where the problem is. So to be helpful to them, and it's not part of the ASTM 283 standard, but to be helpful to them, it's not uncommon that we will fill the chamber. If you look through the glass and you can see it's kind of cloudy, we'll fill that chamber with an artificial smoke or an artificial fog. And what that does is it blows that fog through the holes that cause the leak problem, that cause the failure. And so, I don't know if you can see it, but there's a cloud of smoke or fog billowing out at the top of this upper unit here. And it's really helpful to the owners or to the contractors, because it hones in right away at where you need to focus on adjustments and modifications that you have to make. So, once you've left the field, once you know now with confidence that the system can work, the next option that you can consider is field mock-up testing. So, in the field, what we do is very, very similar, but it's now reflective, hopefully, of both the system and the actual performance of crews who have done it. And we would often try to do maybe more than one, so you can randomly select different areas that have been done by different tradespeople on different days. But anyway, it's all about checking out the workmanship of the guys doing the work on site. But the basic premise is the same. You pick an area that's going to be your specimen. Now, unlike the lab, where we build the chamber with a hole in it and they put the specimen into it, we select the specimen this time, or the Arctic does, and we have to build a chamber to match the specimen. So this is the shot of one of these temporary chambers we constructed on the inside. So it's framed wall with we use a heavy vinyl, so it's possible to see through it. But other than that, it's really the same test and brand. It's called 783, which is the sister field test of the 283 laboratory test. There's the blower equipment, so blower connected to it, an inline flow meter so we know how much air is flowing, and a pressure meter so we know we've got the right pressure, we can measure the flow. So really identical test to the lab we saw earlier. So 783 that we just finished talking about, it also is quantitative. It gets you a number for comparison with a prescription and the standard. ASTM 1186 is qualitative only, and it's used where you're trying to do what they call air leakage site detection. So much like I said we do in the laboratory when they get a failure and we use the fog to help people find out where. 1186 is site detection using, they call it using a tracer gas, but the tracer gas that we always use is just an artificial fog. So this is a new build, construction underway. This is another one of those chambers with the blower unit attached, and you can see through the clear, this is actually clear vinyl, you can see it's completely filled up with fog. And this is just another couple of shots, another chamber filled with fog. There's the fog machine sitting inside the chamber, spitting forth. These units are, if you go to a concert, before you get there about 30 minutes or 40 minutes before the show starts, you'll see these units sitting inside the stage because they want to fill the air with fog so the light show is effective. It's exactly what the system is. It'll fill an arena in about an hour. It'll fill something like that in 2 minutes. This is a handheld one that we have. We wouldn't use that to fill a chamber, but if we have done some of this work and somebody wants to kind of check out specific details, that's often another way that we can be a bit more focused on specific where the fogs have applied. And this is the kind of thing you see on the outside. So, metal and glass curtain wall, for those of you who know it, you'll understand that it's absolutely essential that there is drainage through the snap cap here for any exterior water that got in and around the glazing unit. So, good thing to have drainage, but you absolutely should not see air that is inside the building. That's what this is. It's got fog flow, but that's air that's inside the building flowing in through those holes. So a very, very clear indication that there's something going wrong here. And I really like the fog because if you get into a field situation with the contractor and you say, oh, your number is too high, now there's all kinds of arguments about whether it is or isn't where it is. But when you put fog inside a building and you see that coming out, all the arguments stop. It's pretty clear.
That's something that we use for ductwork too, so it's been really helpful for the project teams and with the blower door testing as well. So for the duct testing, we'll pressurize the duct, and we don't have as cool of a system as your one that fill up an arena, but we've got a party size that we bring, and it's been really effective as an educational tool to show the contractors where the leakage is actually coming from. And then for the blower door testing, both on single family and larger multifamily, to have either a smoke stick or something of that sort where you can see it, visually see it, it drives the home itself.
The fact that you can see the airflow, just the can't argue on it.
Correct.
It is smoke, no mirrors. So I think I've got a series of shots here just to give you some idea. Okay, so this was a field test, and it failed numerically. The quantitative test failed, and again, the contractors now left with where did the actual leakage problem happen? So that's what you see as the assembly when you start stripping things apart. But to the naked eye, can you tell where the problem was? Not that easily. But if you put the fog on it, you start to see where it's flowing from. To your point, when they can actually see the point where it's coming out. There's not much questions as to whether there's a problem or not, but I think it's much easier for them to figure out where they have to go to make the resolution. So here's another example. Under construction, had some problems. Everybody is focusing on the electrical of it, right? For sure, that's got to be where the problem is. For sure. And when you put the fog on it, lo and behold, where the membrane came across the bottom and had to do that connection with the side of the door, it was just a breach of some sort. You could have taken an awful long time with the naked eye trying to find it, but this kind of points it out just like that. Similarly, failure. This was probably not that surprising that it goes there, but that's an operable unit, an operable window unit wall, so not that surprising. But again, you can be ignored and let them resolve. So finally, I'm almost done here, but finally, infrared thermography. It's a very useful tool to be used. It has some limitations, but it's a very useful tool. Basically, thermography, for those who don't know, these cameras are designed to sense energy on the surface they're scanning. They aren't X-ray, so they don't look inside. They can't tell you what's going on inside, what's causing it necessarily, but they can tell you that this area on the surface is a different energy or temperature level than this area. And that, we can use that to our advantage if we're looking for air heating products. We often do it, I shouldn't say often, we usually do it with blower doors. So that's a whole bank of blower doors installed to control the pressure. So we intentionally know what pressure difference we have in the building. And you can kind of get a bunch of different images out of it. Air leakage images are like this, where they're usually fairly, there's sort of like a flare. There's not a regular shape to them because it's air often flowing out, so they're kind of a bit wispy. This is conductive loss, which is normal and so to be expected. So this is thermal bridging for a shelf angle, and that's, you know, I guess we can do take efforts to cut down on it, but to some extent, until they invent skyhooks, we're going to have things like that happen. And then presence of moisture is also something that's just detected by it, because if there's masonry, for example, that has absorbed moisture through the day and it's got warmed up by solar effects, and you scan it that evening, the areas of the masonry that are moist are holding onto that heat longer than the areas that are dry. And so these kind of patterns, that they're not very bright, you know, it's pretty dull compared to the air leakage, but you can kind of see their sort of mottled appearance. That tends to be moisture. But for the purpose of this discussion, it's this kind of thing that we're looking for. So if we're doing an infrared air leakage inspection, what we need to have is we need to have a temperature differential. We say minimum 5 degrees, but the quality of the signature is much, much better as you get colder. Now, our technologists don't like it, because it's not very much fun being outside of the camera at -10, -20, but if the bigger you can make this differential, the better your signature is going to be. But minimum 5 degrees inside out. You need to have the pressure difference across the surfaces you're inspecting. You need to know what that pressure difference is. And the pressure obviously has to be consistent with the directional flow. So here's a shot. In infrared thermography, areas that are warmer or higher energy levels show up as brighter in sort of the red-orange spectrum, and areas that are colder at lower energy levels show up in the darker, sort of the dark blue kind of spectrum. So this one, I almost guarantee you, see how the floor vent is showing up warm, so it's probably actually delivering heat as the image is being taken, but all of this, the dark area, is showing you very low temperature levels. So let's just have a quick look here at, so interior inspections. If you take your imaging from the interior, what you do is you do one where you know for sure using a door fan, so you've got the building positively pressurized relative to outside. So if there's a hole in my envelope, my air leakage is going to be going out. And if I'm scanning on the inside, I won't see anything because the hot air is all going out. So here, under positive pressure, everything looks uniformly warm. And then we turn the pressure around. So now we're negative, so that if there is a hole in the envelope, we're going to suck cold air, at least 5 degrees colder, hopefully more, in through any holes. And the same scan, and all of a sudden you start to see those areas where, it's clearly an area control.
So just a difference in between Celsius and Fahrenheit, that's 40 degrees for us, because you have 5 degrees Celsius.
Different.
Right?
Different, yeah.
So yeah, so that's 40 degrees this side of the border.
Compared to your indoor temperature?
No,
Just converting
I'm just saying,
Celsius
I'm
to
just
Fahrenheit.
converting it. So
5 degrees C can't be 40, yeah.
I just Google said it was. So there.
No, that's probably the conversion from 5 degrees C to X degrees Fahrenheit.
Yeah.
But as a differential, it must be something in the order of
Okay. So it's just.
4,
So I guess just.
4 degrees F or something?
You'll just need a larger temperature difference in order to see this.
There's you.
So because you're not going to be able to see those numbers.
Yeah.
Or that degree of variance with just 5 degrees, I guess is what.
Yeah, fair enough. So if you're shooting from the outside, scanning from the outside, same kind of condition, but on the inside, when we're scanning, we're looking for dark areas. That's the area that's going to flag a concern for us. If you're shooting from the outside now, you're looking for the hot areas, because now what you're looking for is where the hole exists and where the air from the inside that's all nice and warm is being blown out, and it's warming, locally warming the surface, the outside surfaces of the wall. So here's the specimen. The concern was these panels. Here's the overall shot. It turns out it wasn't just these panels, because if you look, there's a problem with all the permanent protection. So all these are bright spots, and you can see how it's sort of flaring. That's all air leakage problems. And if you blow it up, there's a close-up of this panel. And just to be sure, you turn the pressure negative, and there's the same panel. Okay? Same night, same temperature difference, but now negative pressure, positive pressure. And if you look, all the flaring around the panels is gone. There is still some residual heat in the masonry, which is always a problem for us, because you heat the masonry when you intentionally pressurize and you're blowing the warm air out. It heats the masonry up. When you reverse it, it sticks around for a while. So you can sometimes kind of get a bit of a bad conclusion on something like this. But the good news is that these critical problems around the panels, it's night and day, it's clear as well.
How much of an issue have you found to be the radiant heat gain on the masonry in some day?
Well, you have to be you can't scan too soon in the evening. So you want it to be a nice warm day to get everything as warm as possible, but you have to scan at least an hour after the sun has gone down to give the chance to go. And I don't really have it here, but the shot I had about the moisture, if you wait at least an hour, unless it's got moisture in it on masonry, it'll tend to dissipate. And low thermal mass walls, like metal glass curtain wall and aluminum panels, they dissipate extremely quickly. The biggest problem is the heavier thermal mass walls, like the heavy masonry walls, right? Because they just hold on to it for so long.
Since you're taking some angles, what's your experience in, like the photographs we were commenting on earlier, you had heavy, like 12 inches of rock soil, mineral wool. What are you seeing with that time frame? Is that making a dramatic effect?
Well, if you have a very highly insulated wall, then you're going to get the outside cladding probably cooling faster, right? Because it's not getting any beneficial warming through the inside anymore. So the more insulation you have separating from the inside, the more rapidly it's going to respond to outdoor temperatures.
Yeah, I think you quoted that. That's a big one influence clients to make their choice.
So I think the final slide I have here, this was it still is, I think it's in Boston, it's a theater. And like the slide I showed you with the icicles, the complaint was icicles hanging off the underside of it. Brand new build. And icicles hanging off the underside of the whole thing. And so we went to the site with the camera to start with, and it's pretty evident from that. We took video of some of the 1186 fog testing, which I tried to import to run, because the video, I like it because you just see the fog absolutely billowing out of all here. But what's even better is the audio that goes with it, the architect, who's, and he says, so what am I supposed to be seeing? And the fog's just screaming out. So, okay. So anyway, it didn't work, unfortunately. Anyway, so that's it. If there are any more questions that you either want to ask now or later, I'm happy to chat with anybody about anything we talked about here or any other things that might.
Talking about your lab testing on E283 and the field testing 783.
Yes.
What kind of percentage difference have you seen from the same mock-up that you did both between the lab and the field install?
Percentage difference in performance or percentage difference of failures?
Performance.
Well, performance-wise, if you think about it, depending on the way the spec's written, but normally the expectation is that you should achieve the same in both.
Right.
So it's not so much a question of whether you see the performance drop in the field, it's a question of what it took to get to that point. So what I do see, we did a project, a $16 million window replacement job. It was so big that they decided they couldn't single source it in the manufacturer. So they ended up getting supply windows from at least 3, maybe 4 of the big names that probably will know, so I won't name them, but Collier, Oldcastle. Anyway, so they all went through lab testing, and they all had the report, right? Maybe some from our lab and some from others where it says, we tested it and it worked. And 3 of those 4 manufacturers, these are not small fly-by-night manufacturers, these are supposedly premium manufacturers. 3 of the 4 started shipping their product off the production line to the site installing, and we did the field testing. And 3 of the 4 failed. It took them several iterations to get it worked out. And it was little quirky things where somebody on the line hadn't remembered to put a seal on a corner or a certain seam or something like that. So it's very common, very, very common, that the first test in the field fails where the laboratory test passed. Yeah. And it's why I say to people that are trying to keep them on business, but I say to people, they're both really important, they're both really valuable, but one doesn't promise, doesn't guarantee the other. It's why you need to do both. Anything else?
So you probably go testing too. We do moisture testing in the field as well. So you would come out and do air infiltration and water.
Yeah, those are the 2 that are absolutely most common.
Yeah.
Water penetration, and I don't know how much you guys know about it, what's talking about water penetration. There's kind of 2 standard ways of doing it. Far and away, the most common is static pressure. And by static, I mean that we use a chamber. In fact, usually it's the same chamber I showed you. And we create the static pressure in the chamber, and it's just maintained. And it's held, if it's a commercial wall, something it's held for 15 minutes by ASTM 331 days. For 15 minutes, and there should be monitored for the use. There is a companion standard for windows where you cycle the pressure, you keep the water going. So you literally flip the switch on the board unit, let it go down to 0 for a minute, and then flip it back on and do 5 seconds, 4 seconds left. So that's the static testing. My personal preference is the dynamic testing, and you may have seen, I don't know if you can go back, but there are some slides of the mock-ups where we show, up here. So, do you see that one? See what's there? That's a turboprop airplane engine. And it's the one that everybody gets the sexy ones, what everybody really likes to see, because literally what we do, and it's an AMA standard, is downstream of the fan, so between the fan and the specimen, we hang a rack which has all the nozzles on, just do a spray to rain. But you turn the propeller on, and it drives the water at the wall. That's why it's called dynamic. That, for many, many years, was only ever done in the lab. In the very recent past, in the last couple of years, AMA has accepted it in the field, and we now have 6 or 7, they're not aircraft engines, but they're about 6-foot diameter fans connected to a 440 Cadillac turbo engine or something, and the whole thing goes up on a pallet with a telescoping forklift, and it's got the array of nozzles mounted downstream of the fan, and we can test up to 1200 pascals dynamic water penetration in the field. And it's super attractive because, first of all, it's the best simulation of gravity created. Static was developed to simulate somewhat, but it's not the way rain falls. You don't get a static, you get gusts and variations in the pressure. So it's the most accurate simulation. But the best thing about it is you don't need a chamber. So anywhere you can move on the outside of the building with this device, you can run a test. And all you need inside is a set of eyes. So it's expensive to get it to a site, but if you're going to plan to do multiple tests, you can rattle off between a half a dozen and a dozen tests in a day with this device. And there's no disruption on the insides of the build or the occupants of the existing building other than someone walking and looking. Whereas if you try to do 12 areas or 6 areas with a static test, you have to build a chamber at each location, and yeah, it's a real thing. So, yes, we do it, both in the lab and in the field.
Speaking of the afternoon, if that happens in Chicago, you can text me the address, we'll be able to
Oh, well, yeah, there's 3 devices here in the Chicago lab. So yeah, if I know when it's scheduled, I'll zip in a message on you. But you can see the test in the lab. It's the same test as the testing in the lab.
This past year, the terms that you've always heard about durability and resiliency has been a big topic, but the fires that have happened have been a big topic. Is this finding its way to you guys more frequently now?
So our company is heavily involved in the Grenfell Power investigation. We're actually hosting a 3-day event with the UK Parliament at the end of the month, and not me, but the fire guys have brought in fire experts from around the world, and now we're getting together to talk about what needs to change in the standards and whatnot. I'm actually somewhat involved because they're asking me to go and participate to see whether we can somehow start integrating the kind of work we would do on an envelope with the kind of work the fire people would want to do. And the challenge is that they're completely separate camps right now. So anyone who's giving any consideration to how an envelope may or may not perform from a fire perspective is blinders on with respect to these environmental separation issues and vice versa. And it really needs to somehow start to mesh together so that you're looking at the whole picture at once. And I think one of the problems is that in the interest of thermal performance, people have been putting insulation products in walls that have higher performance, i.e. broken plastics, right? And they've been doing that somewhat blind to the fire standard. So yeah, higher R values, but more than the wall. But nobody's ever stopped and say, well, what about the flammability? And the flammability side of it, of course, they're not even thinking about thermal performance. They just think about comfort. So there's a bit of a leader disconnect that we have. The guys are heavily involved to pull those two things together.
Also, I've heard recently that in Europe there's a chain of custody following, so it's not just the manufacturer, it's also the distributor and the contractor who use the materials throughout. There's a circle liability through the whole chain of custody that's now applied. It's not in the US currently. Right? The manufacturer's getting their product tested, and the distributor and the contractor is kind of hiding underneath their small box. But that might be some cross integration of how it goes to the fire department.
I'm told that the UK economy, they believe, is stalled because of this. And how could that be? But apparently, insurance companies won't insure buildings. There's something like 2,200 other buildings that have the same kind of system applied. UK, the insurers won't insure them right now until they've been vetted to be safe. And banks won't advance mortgages on them. So there's no sales going on. People want to get in or out of these properties because funds won't flow. And insurance companies are saying that we won't insure them. So they claim it's having a major effect on the economy because they put real estate behind you, all these assets are frozen. They all have to be studied and potentially modified. So it's a big deal.
I have a question on E283. So I just Googled it and I saw that some recessed lighting was ASTM rated by, or passed by Bureau. So are there a pass-fail criteria that need to be met?
No. ASTM 283 and all the ASTM standards that apply to are procedures only. So it's up to the professional to say, here's the test procedure you're going to follow, i.e. ASTM 283, and they have to prescribe the performance level. So if you're building a building and it's 2 stories high and your use and occupancy is going to be warehouse, you might say, oh, I'm good with a rate of X at a pressure differential of 50 pascals. Okay? But if you're building a high-rise commercial office tower, you'd probably say, no, I need to test at 300 pascals, and I need the leakage rate to be a fraction of X. So that decision as to what the performance criteria, that lies with the design professional. All ASTM 283 tells you is, once you know what you're gunning for, this is how you go about evaluating. But I know there are lots of other standards where there is a pass-fail criteria that doesn't apply to this. I think one of the water standards says that in the absence of anything, here's the minimum, but it's still clear that it's really up to the professional to make a decision on what's appropriate for their job. And if you look at it, it makes perfect sense, certainly from the water, even from the air company, but if you look at it, the amount of water that will hit the face of a tower compared to the amount of water that will hit a low-rise building. And the tower is in East Coast and the low-rise buildings in Nevada. Like wholesale difference in what kind of conditions it's going to see. So it is appropriate that the standard is the same for how you do it, but you tell them what you have to do.
And it can be an assembly or a product, correct? That's it.
Yeah, we typically, if we're just doing a product like a window, we wouldn't use the 283 because the 283 is sort of more for an overall wall assembly. Taxing, I'm remembering now. 547 maybe is for a window, but there are standards for just you can do elements, for example, but if you're doing an overall wall assembly, then you use 283.
I really love the unitized curtain wall system, and of course, in past house, there's glazing portions to assume the heat from the sun. And you have lots of wall assembly questions, you thrive on wall assembly. And with the whole world of closed cell, open cell foam, rigid foams, all those EPS foams, do you have case studies that alert you, like personally, when you see those versus the people that build their assemblies with the mineral wool type systems, foam-free?
Case studies from a thermal perspective, or
It goes for thermal, but also, I think for me, mostly on the fire side. Because the wall assemblies thermally, we can do this very well with the modeling systems that exist, but the fire thing, because you are uniquely qualified in that direction, I kind of curious about that.
yeah, I'll be honest with you, my background and our entire firm, the CLEB background, is all on the building envelope from a separation point of view. So we focused on air, water, structural characteristics. They're the three things that we deal mostly with. Condensation and things like that we talk to, but we don't do fire side. And UL absolutely does the fire side, but we don't. So as I say, in the British situation, we are guilty of that too in North America, where we have firms like ours that are focusing entirely on separation characteristics, and other firms that are focusing entirely on the fire attributes, but not many that look at the whole picture. So UL, now that you're part of the UL group, that's certainly part of their plan is to actually now be able to go to an owner and say, listen, we can do the whole thing. But the expertise on the fire side won't be from me or from my group, it'll be from somebody on the existing UL side who already has that background.
Yeah.
So I personally, I can't help you with it, but you can certainly put me in touch with people if you have specific questions who can answer questions on the fire. And I do it all the time. Now if someone asks me something on fire, I say, I don't know, but what's the question? I'll find somebody who does.
Thank you.
All right, we're going to move on to the research. Between that was really good.
Yeah.
We're going to end the presentation with Mark, but we wanted to give a kind of summary of all of it as just to wrap this all together. If you believe, feel free to grab some more food to don't be setting it up. But I'm going to turn over to Lindsay for
So two things. First, wanted to start off. This little guy in my hand right here does that exact same thermal imaging that you saw up there. You can get it for your iPhone or Android. It's a few $100, and it's not going to be as calculated and precise as some of these. But if you guys are, I don't know how to say that. This is off the top. But just for your own knowledge and for the benefit on your projects, it's something that's a pretty good tool to have in your resource. And also, before I get started, how many people are working on commercial product or projects in here? Okay. Multifamily, single family. Okay, cool. I just wanted to get a sense of how applicable this would be. So, my name is Lindsay Alton, and I run a company called Eco-Achievers. Jason, our fearless founders in the back. Jeff has joined us. We do all the green building certifications, including Passive House for single family and multifamily and commercial. So one of the awesome tests that we have been doing recently is the whole building board testing, and we've been doing more and more of it lately, specifically with the Passive House projects, but also for IECC and for IDA, if any of you have projects that are going through any of those or needing to meet those standards, this test can be helpful with that. So, with the Passive House, the multifamily tests, you have to do two tests. You do compartmentalization testing, which is singular unit, and you also do the whole building test. So, so for instance, in the projects that we're working with Pearl, they will be doing compartmentalization testing as one component, and it's just a single fan, and it tests the connectivity in between the units. So you want to make sure that the boundaries in between and the connectivity in between those adjacent units are as minimal as possible. And there's a threshold that you need to adhere to, which is 0.30 CFM per 100 square feet of enclosure. The next one that you have to do that we were talking about is the whole building testing. And what's required for Passive House is pressurized and depressurized tests. You do the two tests and then you add it up and you get the average for it. It's a pretty big production, not gonna lie. There's a lot, and I've got in the next couple slides we'll show you all the equipment that's involved. But we use one of these two or three panels, shrouds, and you take it down to 50, and sometimes we can get it done in one, and sometimes two. It depends on the protocol. It depends on the protocol that we're testing too. So we had a multifamily Passive House project in Madison that we only needed one fan for. We did some IECC testing up in Lake Forest that we needed two fans for. So, so it really just depends on what aspect. There's also another type of test called a guarded test that some of the standards allow and some standards don't. So ResNet will allow guarded testing, however, it's kind of a gray area right now with IDA, and IECC does not allow guarded testing. So what guarded testing is a combination of both the whole building testing and the compartmentalization specific unit testing at the same time. So the whole building testing is testing the entire envelope. So it's not worried about the cross connection in between the two units. When you do the guarded test, you're taking the entire, everything inside the thermal envelope and you're putting it all, we typically do it at, we typically depressurize. And the reason why we choose that is when you pressurize it, you're more apt to blow open dampers and other things that may have been closed and sealed. So we usually depressurize, and then the guarded test, the singular unit, now we're not worried about this type of leakage. We're only getting the leakage that's coming out of this area. So it's a helpful diagnostic tool to get exactly what you're looking for a specific unit.
Do you do this a single unit on each single unit?
For Passive House or for?
Right, for this testing, as opposed to the whole building.
So
you
usually,
test each unit for its.
So usually, if we're doing the testing, if we're doing it on a whole building, we would have some sort of sampling plan in place. IDA does not follow the same ResNet sampling plan. They have their own system for how many units and what types of units they want tested, and then IECC does not allow sampling. So just, I would say be aware when you have to adhere and conform to the different standards, which one you're specifically going for, because that will determine how many tests you need to have done. So the preparation in it, and if you can't read this, this was kind of a funny little cartoon. I think my spell checker is broken. It keeps changing luck to preparation. And that's a big part of it, is making sure that you're fully prepared for the test that you have to do. It's a big procedure, especially on some of these very large buildings, making sure that you've got the right amount of fan, blower door fans, tubing, wireless. You never know when your wireless might kick in or kick out, so you have to have a backup for that. Connecting with different tradespeople, having the building set up in the proper way to make sure that you're getting the right leakage, you're showing the right amount of leakage. And this is a little sense of it. So multiple blower doors. If you're doing the compartmentalization testing, we often do that in conjunction with a duct blaster test because we don't need the capacity that a huge fan can do, but hundreds and hundreds of feet of tubing, multiple tubing, having a cart to go with it, and routers. It's been, to be honest with you, it's been really interesting to put everything together, and it's been cool as a team to be able to practice and see how the different buildings are performing. Okay. So for the testing, everything that the condition of the building, if you have a continuously running intake or exhaust, you can seal that off. If you don't, it's left open. So the dampers are left to perform on their own. If you don't have dampers in certain intermittent systems, you can't seal them off. So so that's why the coordination with the different contractors is imperative, because the building team doesn't always know how the mechanicals are running, and to be able to seal off everything that's needed so that you have the right final test is needed. So, and yeah, this was just a project where they sealed off the intakes on the exterior, and they ended up having to get a crane in order to have that happen. This was not one of our own projects, but one of our colleagues. And that's kind of it. So basically where we're at, so ICC, we're now in 2015, so that's the blower door figures that are being required, and we're at 5 ACH for, even though we're in climate zone 5, it should be at 3 ACH. Our passive house numbers are 0.05 per CFM, or 0.05 CFM per 100 square feet of enclosure, so it's not the direct volumetric ACH configuration, but it's more of the surface area is what we're testing. And so, but these tests are a core component of all these different certifications as you move along the line. Questions? So yeah, so just to recap, for the passive house specifically, your single family homes are going to have to meet the 0.05 ratio, and then the multi-family projects are going to have, for the whole building, it's the 0.05, and then the units are 0.30.
I just have a quick question again about the guarded test. Is that a situation where, in like a recap, would that be effective? Because at that point, then you're just isolating the envelope itself. Is that a situation where that would be helpful, or you're just saying in general?
Yeah, so so it depends the extent of the rehab, whether or not that testing is needed. If you're changing, if it's an existing building, you're changing the amount of energy that's been used, or that the building is using, then you will, according to the state energy code, you are supposed to have that building tested. And yes, that guarded test is helpful for you, especially if you're hired into a situation where you haven't really had the ability to air seal as much. It helps minimize the leakage that is happening, that will be needed for that particular unit.
Essentially, inside the building itself, right? So envelope in some capacity, then you can kind of negate the leakage between them. Is that true? Sorry, I'm just trying to understand that.
So the Garnet test.
Or is it the opposite? Sorry.
Yeah, so the Garnet test basically, so it's only going to test that unit and it's going to negate so even if you didn't well seal the demising wall, and some of the penetrations through the demising wall, or if you have any leakage that is happening through like interstitial anywhere, it negates all of that because the entire building is taken down to the threshold, the Pascal threshold that it used to. So then once that individual one kicks on, then you know that that's just the leakage that's happening out that exterior wall, not what's happening on the inside.
And you're saying IDA doesn't let, this isn't something that
IDA's a little bit gray on that right now.
I think, actually, we have an IDA project where we have to qualify to see if we're not touching the putting insulation and doing that windows in our house situation. And we have to qualify, we can't guarantee the order if they're going to pass because we are not.
In some of them, if they're historic buildings, they can get an exemption for that. So, yeah. Okay.
So yeah, it's interesting.
And I would say in that case, just get very clear direction from them on what's expected and what you can do.
Yeah, I think that they accepted a certain amount. I did construction not. I remember that being a huge concern of ours because we were essentially saying that we're pretty sure we're going to be failing the leaks through the right dimensionals, right? Because we are not touching this.
And that's what's been helpful for the IECC testing is that they'll allow the whole building testing versus in addition to the unit by unit test. So even in some of the like one of my new construction projects, by the nature of the assemblies that they decided on, it was just inherent that they were going to fail compartmentalization testing, so unit by unit testing. So we suggested that instead of complying via compartmentalization, that we would do the whole building, and they actually came in at like 1.5 ECH because the volume is so huge that the amount of leakage has less of an impact.
All right. If you have any more questions, feel free to come up and see Mark and Lindsay. But just to wrap up, thanks for everybody for staying later and for great questions. And thanks to these two presenters for a great presentation. Mark's going to guide us to where we're going to grab some drinks, but our next monthly meeting will be on the 21st, and it's going to presenters will include the mayor's office, the Department of Buildings, AIA 12 Passive House, and AIA 2030, and we'll be talking about how us as an organization can help the city meet its carbon reduction targets. So it should be a really good presentation. It will be a ticketed event, so if you're a Passive House member, it will be free, but if you're not, it will be a small fee, but all the more reason to become Passive House. Yeah, so we'll go grab a drink, and thank you, Sean, again, for hosting.
I'll play that. And then, yeah, for next month, this is a retractable wall, so we can take up 2 classrooms, and if you make the video, we can take 3 classrooms, so the wall goes up with that. And then, yeah, just a reminder, please take some food and some cupcakes home if you can. There's plates and napkins to cover your food. So feel free to stick around for a little bit and eat too. So
Yeah, please share with your contractors, architects, clients, designers, third-party verifiers that we do meet the third Wednesday of every month at this facility now. We are new hosts. So it's up to all of us to share that news. We're all volunteers. We don't have a marketing team, even though we have great marketing people. So please share that, email email, phone calls, person to person. Tony did put me on the spot, by asking me where we're going. I am logistically challenged. I can handle the buildings, I can't handle the transportation. I would like to defer to Jason and Lindsay as they live down the street from here to their offices, if you guys have an idea where to go.
There's also,
Takes the pressure off.
You have pressure, guys.
you have Cobra, but that's further this way, or we can go down to Fulton or Randolph, you know, anywhere of those. So I think what we might be able to do is just start packing up and everything, and,
That's the closest.
we can do it.
There's one,
quick little-
yeah, bottom line's on the left. It's a nice big,
It's right across the street from the Titans.
yeah, right across the street, 2 blocks south, perfect, bottom line.
Bottom line.
Everyone in America needs to give directions based on the comment.
So Lake Street is 2 blocks.
No, I know it is, I'm just joking, but everyone in America, people give directions based on what, how